So in this unit, we're going to look at higher degree polynomial functions and also how they relate to what we've already learned. So first, let's take a look at this function right here, y equals x to the fourth, and then explain how does that graph shift using some of the rules that we've already learned. All right. Okay, so first I'm going to graph this for you, x to the fourth. So here's our graphing calculator. X to the power of 4. See what it looks like? It looks very similar to x squared. In fact, let's compare it to x squared here. X squared. Okay, so you can see x squared in the red, and you can see x to the fourth. Very similar shape. You could describe some differences here. It kind of flattens out when x is near 0. It's a little narrower. So let me delete this again. Let's talk about the behavior of the graph right here compared to what we've learned last semester and this semester as well. So if you have x plus 3 in parentheses, how do you think that shifts the graph? We'll think back to other functions that we've looked at, and we know that x plus 3 shifts the graph. And I'm going to pull all these up here. This would shift the graph left 3. So it's going to let me write. Okay, hold on. Here we go. So this will be left 3. The minus 3 on the outside of the parentheses would be down 3. The 4 on the outside would be up 4. And the negative in front of the x to the fourth would make it upside down. Kind of like the slope. So upside down this way. The 0.5 would make it wider. And the minus 1 on the inside of the parentheses would make it shift right 1. And remember, if you ever forget any of the transformations and you have a graphing calculator, you can graph the parent function and you can graph the shifted function to see how it shifts. Okay, let's take a look at the next slide here. Okay, so here's another transformation. We have f of x equals negative x to the fifth. So here's what an x to the fifth function looks like. And we're going to talk about in a few other slides what the negative is doing to this function. And, okay, here's one that we already talked about. X plus 1 to the fourth power shifts it to the left 1. So you can see here's the new vertex and some points. But let's look at behavior. So in class, here's the investigation we're going to do. So we're going to break it up into tables. One set of tables is going to graph all the even functions, so x squared, x to the fourth, x to the sixth, x to the eighth, and then they're going to answer questions 2 through 5 in your notes, and we'll talk about those. The odd tables will graph the odd functions, and then also answer questions 6 through 9 in your notes, and then we'll answer those together. Okay. So basically, here's what it goes over. An even function is parabolic in nature, so it's U-shaped. A U-shaped graph. Here again, here's an example of x squared and x to the fourth. And the higher the power of x, the more it flattens out near 0, where x is 0, and also gets steeper. So let's take a look at that on the graphing calculator. So this is what you would be doing in class. So let me graph a few of these. Let's do x to the power of, how about 6? X to the 6th power. So again, it should flatten out more, and let's see what else it does. Flattens out, and it gets steeper. Let's do x to the power of 10, just to see what happens here. Oops, I have to hit tab first, sorry. X to the power of 10. Again, you can see it flattens out more and becomes steeper, so it's the black one. All right, so there's an example of even functions, U-shaped pretty much, but they kind of flatten out and become steeper. So let's delete these. Let's look at odd functions. All right, so an odd function, x to the power of 3 is odd. Oops, again, I forgot to hit tab. X to the power of 3. Let's do x to the power of 5. Oops, tab. X to the power of 5. Again, you can see it's kind of flattening out, becoming steeper. X to the power of, how about 11? Oops, again, tab. X to the power of 11. Ooh, that's too many. okay? Again, it kind of flattens out, becomes steeper, and you answer those questions in your packet. Okay, so behavior graph, if it's an even function, oh, I guess I'm supposed to write on here. Let's do that. Okay, so in an even function, the higher the even power, the skinnier we can say it gets, so it becomes skinnier. And near 0, where x is 0, it flattens out. Okay, so there's the behavior of even functions. And if you look, we'll look at something called end behavior. But if you look at the end behavior, we say right here in end behavior, and again, we'll approach this again, but as x approaches negative infinity, so all this means is x approaches negative infinity, as x goes to the left, then what is happening to the end behavior? Y, the y value approaches positive infinity, and as x approaches positive infinity, so all this is saying as you're going to the right, y approaches positive infinity. So the end behavior in even functions is the same. You're going up in each direction for an even function. Let's look at odd. So in an odd function, again, the higher the power, the higher the odd power, again, the steeper it becomes. And again, it flattens out where x is 0. We can talk about end behavior here. As x approaches negative infinity, all it means is it's going to the left, the graph goes down. So we say y approaches negative infinity. And as x approaches positive infinity, as you go to the right, y approaches positive infinity. So an odd function, the end behavior is the opposite. So it starts down at the bottom, and then it goes up. There's the end behavior for odd functions. And again, we'll talk about that more in the presentation. There's something called a lead coefficient test. The graph of any polynomial function eventually rises or falls depending on the leading coefficient and the degree of the polynomial function. So I wonder if that's all for this. Okay, so here's what it means. This is an even function. You can tell by the end behavior as you go to the left. There should be a negative infinity. As you go to the left, oh yeah, that's right. This is y, f of x is y. This is saying as you go to the left, y goes up. As you go to the right, y goes up. So if it's an even function, the end behavior is the same. This is also an even function, and the end behavior goes the same, but this is when you have a negative. So for example, this would be y equals a positive value in front of x to an even power. And this would be y equals negative x, as this is an even power as well. Okay, so if it's even, the end behavior is the same, but if it's negative, it's upside down. Just like think about the parabola that was negative, and if it's positive, it goes up in each direction. And again, these symbols right here, as x approaches negative infinity, means as you go to the left, y approaches positive infinity, this means you go up. As x approaches positive infinity, this means as you go to the right, then you go up. Okay, so the end behavior is the same in even degree functions. In the leading coefficient, if it's negative, it's upside down. So for odd functions have opposite end behavior. So right here, if you have a lead coefficient that's positive, then it starts down and it goes up. If you have a lead coefficient that's negative, so this is again odd, it starts up, but then it goes down. So here's what it means. As x approaches infinity, so this means as it goes to the right, our graph goes up. As x approaches negative infinity means as you go to the left, then our function goes down. And here, as x approaches negative infinity as we go to the left, our graph goes up. And as x approaches positive infinity as we go right, our graph goes down. So for odd functions, they end differently, and it should start down and go up if it's a positive lead coefficient, but if it's a negative lead coefficient, it starts up and then it goes down. We'll also talk about the, okay, so here it is, lead coefficient test. We talked about that. So in a table, here it is. If it's an even function and the lead coefficient is positive, here's what it looks like. And as you go to the left, so as x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches positive infinity. So they go up. If it's an even coefficient and the lead coefficient is an even function and the lead coefficient is negative, it's going to go upside down. And so this is opposite. So we should say as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches negative infinity. Okay, or we can just draw arrows. So to the left, as x approaches negative infinity, x approaches positive infinity. This is going to go up, this is going to go up, this is going to go down, this is going to go down. That's easier. All right, so for an odd function, if it's a positive coefficient, it looks like this. So as you go to the left, it's down, right, it goes up. And an even function down here, an odd function, if the lead coefficient's negative, it starts up and it goes down. So this would be up, this would be down. So this table will help you today with your assignment where I ask you the behavior of an even or an odd function given the lead coefficient. You should be able to tell me if it's going up or down for the end behavior. Describe the right hand and left hand behavior of the graph. So here's an example of what you would see on your assignment. All right, it is an odd function with a negative lead coefficient. So this is when it starts up and it goes down. So we say as x approaches negative infinity, y goes up, positive infinity. As x approaches positive infinity, y approaches negative infinity. Okay, so there's an example of what you would see on your assignment. Here's another one. So we know it's an even function and it's a positive, so it's going to look something like this. So as x approaches positive infinity, so does y. As x approaches negative infinity, y approaches positive infinity. There's the end behavior. And we can see what the function looks like right here. Okay. The zeros, also called the solutions, the x-intercepts, the roots, we talked about that last unit. We're going to do this graphically. Okay, so the roots right here, if it's degree 3, you can see from the graph there's 3 zeros. If it's to the 4th power, guess how many zeros it has? You can see that it has 4 zeros. A function has at most n zeros, and the graph has at most n minus 1 turning points, relative mins or maxes. So from this graph right here, again, it has 3 zeros, which means it changes direction n minus 1 times, so 2 turning points. It changes direction twice. And again, here's the graph. 3 zeros, it changes direction twice, it has 1 max, 1 min. And we say relative max and min because it has, you can't see the absolute max or min because of these arrows. And again, degree 4 has 4 zeros, has 3 turning points. There's something called repeated zeros with an even multiplicity. What that means is if you were to factor the function, so we factor this and find the zeros. Again, this has 4 zeros, but one of them bounces off the zeros, and it bounces off the zeros if one of the zeros is repeated. So for example, this right here, if we solve this, we're the zero product property. We set that equal to 0 and solve for 0, divide by negative 0.25. X squared equals 0, take the square root, x equals 0. Well, at 0 right here, since it's a squared even multiplicity, it bounces off this 0 right here. So with an even multiplicity, the squared, it's going to bounce off the 0 after you factor it. Here's another example. So they took this function, they factored it, and here are the zeros. X would be negative 1 as a 0, and you can see that right here. But there's a double zero, a double root at x minus 2, in other words, a 0 of 2, and here's that 0, and since it's a squared 0, even multiplicity, it bounces off that 0. Okay, so it bounces off the even zeros, repeated multiplicity with even. If it's repeated an odd number of times, so again, they factored this, they pulled out an x cubed, so this x cubed equals 0, and here x equals negative 2 is the other 0. So we can see that at 0, it goes through that 0. So here it goes through one of the zeros. But if it's an odd multiplicity for the 0, it goes through that 0. So if it's an even multiplicity, like if this would have been an x squared, it would have bounced off the 0. But since it's an even multiplicity, it goes through. Last type of problem. When sketching a graph of a polynomial function, you need to find the zeros and the y-intercept. You can do that by graphing. Apply the lead coefficient test. The lead coefficient test tells you the end behavior. Does it go up? Does it go down from left to right? What does it do? Plot a few extra points. You can draw the graph. So you can use your graphing calculator to sketch this function. So that's what we would do. I'd pull up the graphing calculator. I would expect you to graph that function with the graphing calculator. So do those problems in class first if you don't have a graphing calculator. And if you don't have a graphing calculator, remember at home you can use that www, I think it's Desmos calculator, or maybe just search it. Maybe it's not www, but use the Desmos calculator online if you have an internet connection, but not a graphing calculator to graph those functions. Here's the last type of problem. Find a polynomial of degree 4 with these zeros. And we know that this should have 4 zeros and 3 turning points because it's degree 4. So if the zeros are -2, the factor is x plus 2. If the 0 is 4, the factor is x minus 4. And if the 0 is 7, it's x minus 7. But that's only 3 zeros, so we have to square one of these to get that last 0. So you can square this one, so it's 2 zeros here. You could square this one, or you could square this one, and that would give you 4 zeros. It doesn't give you enough information. So you can square any one of them to give you the polynomial that you want. And I wouldn't expect you to simplify. You could leave it in factored form. All right, so there's a lot of information here. On your assignment, you're going to practice graphing with your graphing calculator, telling me how many zeros it has, maybe finding the factors, and looking at end behavior.